第一个把 introduction 跟 coalescence 把它 combine 起来，然后讨论 coalescence model 跟 statistical model 的关系，还有跟 transport model 的关系。这个最近很多人，尤其申凯嘉，还有王瑞啊，还有很多人都在讨论 coalescence 跟 transport model 到底什么关系。然后后来也有人 interesting coalescence model study hypertriton， 但 hypertriton 我们知道是马玉刚跟他的还有陈建辉他们最先发现在黑方颗粒里面找到的 hypertriton， 所以这是很重要的一个 light nuclei produced in heavy collisions。然后来我要讨论的 coalescence model， 讨论这个 nuclei small systems， 这个 I think 是孙凯嘉最先 realize coalescence model give a natural explanation of nuclei production of small systems。那最后来讨论这个从这个 density fluctuation 跟 nuclei production 之间的关系，这个东西的原来是徐长波的 idea， 然后孙凯嘉跟陈立文 pick it up， 我就 join 他们。最后给个 summary。Let me see。它不动了。OK， 那我从 coalescence model 的 history 开始，很快的讲说，在1963 Butler 跟 Pearson 他们在 study baryon 8打一个 target 在很高的能量，发现了 neutron productions。那个同时有两个 group， 是 Butler 跟 Pearson， 还有一个 Schwarzschild 跟 Trupancic， 他们的 paper 是前后两个接到的836、854，他们就发现这个 neutron production can be described by two nuclei coalesce into neutron with the nuclear matter acting as a catalyzer. You have to conserve the energy momentum through the nuclear matter, the mean field, right? In the picture shown here. But the point is the neutron number is proportional to the proton number square with half the momentum. Schwarzschild and Trupancic have the same idea that the neutron number divided by the proton number related to some phase space volume in the momentum space that around the proton, right? So that's the first pioneered work on coalescence picture of neutron productions. Now, this is from their papers, figure 3 from Butler's paper, figure 4 from Schwarzschild paper, right? So this is the proton spectrum, that's the proton, they're same reactions. It's the baryon 8 acting incident on with energy of 30 MeV, the proton baryon 8, 30 GeV proton colliding with the baryon 8 target. One look at 45 degrees, the other look at 30 degrees. So 2, the solid line is the neutron yield in both cases. The 3 is the coalescence models calculations. So in the Schwarzschild model, you have a parameter, right? So the rho is the parameter. In the Butler's model, of course, he has to just write on this relation here, right? Then after more than 10 years, in 76, when Beverlek started to run Hevian experiments, and Hans Gutbrod, that time, his origin from GSI, I think he spent a lot of time at the Beverlek. They do the experiment with the neon 20 scattering from uranium at 2 energy, one 250 MeV per nucleon, the other 400 MeV per nucleons. They measure both the deuteron, triton, helium-3, and helium-4 for the both energies. And the black dots are the experimental data that's very accurate. You see the arrow bars are very small. And the solid line are given by this simple coalescence formula. So the number of light nuclear production, the momentum spectrum is related to the proton spectra to the 8th power. And the proton momentum is a fraction of the light nuclear momentum. And the BA is the famous coalescence parameters. It's related to this coalescence volume in the momentum space. And they can fit the data very well with the radius of that momentum space volume. It's very insensitive to the collision energy, right? They are very close. And actually that momentum is reasonable size, because if you take the inverse, give the radius, right, 120 is about 1 Fermi or so, that's a radius, right? So that's about a little bit smaller than the neutron size, very reasonable. So that is the, people start to enter the coalescence model again during the Beverley era. And at the same time, right, after the coalescence model was found to work very well, that time Kapusta and the Siemens, Kapusta was just graduated from Berkeley. He was spent a few months before he went to somewhere for a postdoc. Now, Phil Siemens was originally at the Newsport Institute. He was on sabbatical leave to spend some time at the Berkeley. So they talked to each other, wrote a famous paper. They said one studied the neutron-proton ratio, one can find the equation of state of nuclear matter. Their idea is very simple, because the neutron-to-proton ratio depends on the entropy of the system, of the hot matters. If you can measure neutron ratio, you can determine entropy. Now, if you find entropy is too large compared to you expected from a normal nuclear matter equilibrium state, then it may indicate some other phases of matter produced. And look at on the left-hand side, right? There's a DP ratio, right? There's experimental data. The side line is the fit to the, right? The Braswell model fit, right? So from DP ratios, then they can extract the entropy, right? Look here, that's the entropy per baryon, per nucleon. And the measured entropy is large. Entropy about 6 units per baryon. Theoretically, use the normal nuclear state to give you something either 3 or 4, between 3 and 4, so lower. So the extra entropy produced during heavy ion collision at the Beverley, they claimed at the time. So that's why they said, right? They observed the paucity of neutrons, suggest that strong attractive forces are present in hot dense nuclear matter. All that degrees of freedom beyond nuclear and the pion may already be realized at excitation of 100 per baryon, right? So that is a very provocative claim. That time the collision energy device, it's only very low. It's either 400 MeV per nucleon, 800 MeV per nucleon. So normally one wouldn't expect the possibility of form QGP, because the maximum density reached, if I remember, roughly a few times, 3 or 4 times normal nuclear matter on the borderline, right? At 800 MeV per nucleon, you reach about 3 times normal nuclear matter density. But at that density, if you capture the energy density, almost half 0.5 GeV per cubic Fermi. That's about the transition energy density at the RIC. Right? That's about a half or so GeV per cubic Fermi. So maybe that's something going on already. The argument is very simple. I'm not going to go to detail, just tell you what's the argument, right? You can easily calculate the entropy per nucleon. In a assumed nucleon, they are interacting. Then you can calculate the entropy per nucleon given by 5/2 minus the nucleon density times the thermal wavelength, right, of the nucleon. Then you can calculate the DP ratio, right, for the same nuclear matters. The DP ratio can be expressed related to the nucleon density and the thermal wavelength. Therefore, entropy per nucleon equal to 5/2 plus these factors minus log RDP. So it's 3.95 minus log RDP, right? That's the non-interacting one. Now, in the previous slide, we know that the ratio is very small, 0.1 or so. So this is a negative number. So the log ladder doesn't become very, very large from measured one, right? If there's no neutron, then you have a 4, That's why I say no deuteron, you have 4. Once you have a deuteron, then you can go up, right? And that's why they said they claim that additional entropy produced during heavy-ion collision at the buffer energies, right? So that gives more motivation for people to study the properties of the matter produced in heavy-ion collisions. So that paper was very important at that time. And after a couple more years, 79 to 96, that's almost 16, 17 years. And that time, because we got AGS, that energy got much higher. The AGS, you're talking about GeV rather than 1 GeV, almost 10 factor 10 higher in incident momentum energies. So those are all the measured, the proton and the deuteron, right? You have a deuteron produced from the EA802 collaboration. And at that time, that's a transport code called a relative cascade code. And that's developed by Kahana. And so he fitted the proton spectrum very well, just a simple cascade code. Then he used a coalescence model, right? And this coalescence is a little fancier than Butler-Peterson's model, also a little fancier than the Gutbrod used in terms of coalescence parameter. That's a really microscopic coalescence where you project the nucleon wave functions into deuteron wave functions. And he got very good descriptions even at that time, right? So that is 1996. And then we go forward another 20 years, right? That's 2015, when Kai-Jia Seng and Li Wen-Chen, right? They also look at the using coalescence model study the light meter production at RIC, go to 200 GeV at the middle of PTTs, and the data are given by Phoenix and the star are those symbols. They use a blast wave model to fit the proton spectrum, then they predict the deuteron and the helium-3 and so on, their yields. They found that using the realistic coalescence model I discussed very soon, like a Kahana, right? So you got deuteron correct, helium-3 is correct, but alpha particles somehow they under-predict. That's the normal coalescence model. And in order to explain data, they claim maybe alpha particle are produced at an earlier time than triton or helium-3 or deuteron because they have a larger binding energy. Therefore, we can produce earlier than phase out. Therefore, right, so they use that binding energy effect. Oh, sorry. And let me just a second. Right. So the red one is FO2. That means you see you have a smaller radius. FO1 is the blue one. It's lower than measured alpha particle. That's a larger radius. So that because they claim alpha particle, the binding is larger, may be produced earlier, even in the coalescence model. I think that's a very interesting idea, right? Then they said that if you apply same ideas, you can expect to enhance the production of lithium 6, lithium 5, and so on, right? Well, let me see. At the same time, right, about same time, when I was in Chengdu with Li Ling and her students, and that time I got a phone call from Shucraft from LHC. He said, well, we have measured the light nuclei V2. Here are deuteron, helium-3, the V2, those are the symbols are the LHC data. He said, what are your predictions for using MPT models? So I told Li to do the MPT calculations. So indeed, we get the deuteron proton number very well. Or use Blackswave. That time with the Blackswave. Sorry, we didn't use MPT. Later on, we used MPT, right? So use a Blackswave model. Somehow we get the spectrum right. That's a proton, deuteron, and the helium-3. But we have a problem with the V2, right? If we use the normal coalescence model, then we get the V2 increase faster with PT than expand measurement. Then my student, Ethan Sen, at the time, he said, well, if we introduce some idea like we suppress high momentum, here's the flow are better described after allowing nucleons with a momentum larger than 1 GeV, more spread in space when the momentum are more aligned along the reaction plane. In other words, try to reduce the coalescence probability to get a small V2. And that is introduce a two parameter. One is the A, the other is a P naught, to modify the spatial distribution of those high momentum particles, right? But we never eventually go on try to check whether this condition is indeed taken care of in transport model. I think we should come back again to look at the transport model which can reproduce the experimental V2 to see whether that's momentum space correlation is present in the dynamic model or not. At the same time, see, that's 2016, I saw a paper by, I should say the name, right? That is from Yugan's group, right? They studied the deuteron and helium-3 and the triton V2 as a PT at many energy, 200 GeV, 62.4, all the way down 7.7. And Yugang and his collaborator claim using MPT plus coalescence model, the coalescence release coalescence I discussed in a moment, can reproduce data very, very well. But if one use a blast wave model, it fails, right? And maybe that's the same reason. The normal blast wave model, one needs somehow this kind of additional moment space correlations, but that in the AMPT model, somehow it's automatically there. Maybe that's a reason, I don't know. Yeah. But anyway, they can describe, they use MPT plus coalescence can reproduce data very, very well. And at the same time, right, when Bin Zhao, at that time he was a student of Hui Zhao, and then we used the hydrodynamic model, Vishnu, using event initial conditions, and then followed with URQMD, then use NPT initial conditions, then do the release coalescence. Then we get a good description of all the proton spectra for the Alice data, 2.76 TeV. Also for the deuteron, they do very well at both energy, 2.76 and 5.02. And for helium-3, the data is let me see which one's the data, right? The data is the helium-3 at 2.76. And the theory is a little bit lower, right? I think at that time we debate whether helium-3 can be produced as a two-body coalescence or three-body coalescence. Two-body coalescence is a deuteron coalescence with a proton make a helium-3. A three-body coalescence, two proton neutron dual coalescence. I think it here just including one of those, not both of them. So in a way, this one somehow consistent. They didn't look at the V2, but in the paper they didn't look at the V2, but here they check it, even for the V2, they can also satisfactorily describe. So it's consistent with the Yugang's study using MPT at RIC energies. Now let's see how the coalescence model compare with the thermal model, right? Now, that's the thermal model is well known, right? Invented by Peter Baum-Benzinger and his collaborators, including Lu Xu at that time. They said everything yield of all the particles fixed at the chemical freeze out at the TC around 156 MeV. and then you can calculate the particle yield relation. Once you know the volume, you can know the yield. So you get the very descriptions of all the particles from pion all the way to alpha particles, right? That's about 9 order of magnitude. So statistical thermal model system works very well for describing nitrogen productions. Assume they are produced at chemical phase out or hadronizations. So the question, but the coalescence model is based on the assumption nitrogen are produced at the kinetic phase out. Thermal models assume that nitrogen are produced at the chemical phase out. How do we reconcile the two? So let's go back to study the coalescence model explicitly. The coalescence model is based on the certain approximations. So initially for them, the neutron examples, there are 2 nucleons, proton, neutron, that's the wave functions. And then after when you form neutrons, then you calculate the projection of the wave functions. And then, so you have the wave function of the 2 nucleons. Therefore, you have 3 Wigner functions, Wigner of the proton, Wigner of the neutron, and the Wigner function of the then you can do the standard calculation. I just skip all the details. Now, the main point in all the coalescence model, you pretty much 3 Wigner functions, right? Proton, neutron, and the deuteron internal wave function, it's Wigner function. But in normal, what our calculating, we make assumptions, right? We assume some of the nucleon Wigner functions, the delta function in space and the momentum. That's assumptions, right? Actually, that violates a certain principle, and therefore also violates unitarities. That means if your deuteron number is large, if you don't treat properly, there's no bound. The total probability will be greater than 1. But that's what we normally do in the coalescence model. And the Kahana, he called this one is the standard Wigner calculation. That means treating the nucleon proton Wigner functions as delta function in the phase space. In the really quantum Wigner calculation, you have to use wave packets, right? Instead of a delta function. That wave packets, you have a spread in the coordinate space or the spread in the momentum space. In that way, you guarantee unitarity is preserved. Right? But for small number of deuteron producing events, the standard calculation is a good approximation. Right? Then that's okay. Once you use this coalescence model, we can calculate the deuteron number. So I like to spell the detail. You just follow, right? You got deuteron number. You have the nucleon distribution, proton distribution, neutron distribution folded with the deuteron internal Wigner functions. If you assume the nucleon has Boltzmann distributions, and you know the fixed number by the fugacities, right? Then you can compare the deuteron number from coalescence model versus deuteron model in statistical model. So I skip the details. If you're interested, you can read my slides. Then, of course, you have to go to the relative coordinates to project the wave function, the proton-neutron relative wave function, projecting the deuteron relative wave functions after you're done, right? Straightforward algebra. So that is the deuteron number, right? So, and once the proton number and the neutron number, that's the volume of your fireball. There's a temperature of the kinetic phase out, all right? And this formula is given by here, right? Depends on the volume, of course. And the sigma is the width of the deuteron internal wave functions, right? And if I assume the thermal wavelength is very, very small than the width of the nuclear width, then you can drop this term, so this becomes this one. And this formula is very similar, can be converted into thermal model expressions, right? So once I have these numbers, then I can replace N1 and 2, right? In terms of the fugacity of the proton neutrons, right? So I know the proton number, neutron number, once I know volume, I know the fugacities, I can express it into fugacities, right? So I rewrite this one in these formulas, right? And also compare thermal model. Now I do the thermal model, right? The same thing, the thermal model, you just Boltzmann distributions, you have a fugacity, you get this one. So those two formulas are identical except the binding energy, because thermal model takes the neutron mass into account. So that's a binding correction, but it'll be these two MeV, T is about more than 100 MeV, therefore this is equal to 1. So they are identical, therefore thermal model and the current, they are identical, right? The only problems, right? In the thermal model, we calculate the TC right? And why the thermal model TC the same as the thermal model TK, but this is the TK. Thermal model TK agrees with the thermal model, the coalescence model calculated with the TK, but Peter Bromantz is thermal model the TC. So why they are the same? Here, right, you have chemical potentials, the fugacity. Here, there's no fugacities, right? That's why they can equal, right? And I think I can skip those details, right? To understand that, I think I got Zhongxu to work on this one. Like if according to Siemens and the Kapusta idea, right? If the entropy during hadron evolution doesn't change, if the only baryon-rich matter, there's no pions, then the baryon entropy per baryon is a constant, and the guaranteed D over P ratio doesn't change. But in heavy ion collision, that's the case. Not the case, that, right? Because we have an entropy productions because you produce many pions. So, for example, you look at the 200 GeV H700 MPT, he looked at entropy, right? The baryon entropy turns out doesn't change very much during hadronic phase, but the pion entropy increases, right? So the baryon entropy doesn't change, and that tells you the DP ratio. Once Rich determined that the chemical phase out during hadron doesn't change because the baryon entropy per baryon doesn't change, although the total entropy increases because the pion being produced. Right, that resonance decay into pions. That's produced those entropy. So even at the high energy collision, it's the lots of pions that carry most of the entropy, and that increases with time during the hadron evolutions. But for the baryons concerns, their entropy per baryon doesn't change, right? It's a constant, and that's all consistent with the Siemens and the Kapusta's idea. If the entropy doesn't change in the baryonic matters, then the DP ratio doesn't change. So that's why in a transport model way to understand why, or do the thermal model calculate the TC and the thermal model calculate the TK, they are the same because in TC there's no chemical potentials. In TK, everybody has a chemical potentials. But from here to there, right, the entropy per baryon remain constant. Right? So that's some, I think, give a plausible explanation of why the DP ratio is determined at the TC, already determined at TC, and never change afterwards. Let me skip that one, okay. Then, the one time almost 12 years ago, 13 years ago, when Jan Segall was me, that time I was interested in what happened because the Phoenix measured the deuteron V2. I said, how do I understand the deuteron V2 using coalescence model? And also using transfer. So we started putting the deuteron production dynamically in the art part of MPT. So I think that's a first model calculation, microscopic model calculation, including deuteron as a dynamic decrease of the hadron evolutions. Because we don't have the three-body scattering, so only include MP to D pi and D pi MP, the two-body reactions. Unfortunately, that costs tiny, but that costs only 10 millibars, right? So after we include that, we can look at how the deuteron and the proton evolve in time to the hadron evolution. So the black dots are the proton emission time distribution from ARTS. At Rick, I forgot to put what, and I think 200 GeV, right? Well, I run MPT, then at start counting the proton emission time, right? So the proton non-emission time Most of the protons emitted are 5 Fermi after hydronization, 8 Fermi after hydronization, but it can range all the way from 8 all the way to 25 Fermi over C or so. Right? For deuteron, right, or dynamic, well, NP goes d pi, then pion can destroy a deuteron into NP. So the deuteron emitted from the dynamic reactions are given by the red curve. They are not identical, but they're close. Right? And they are both are very close to the proton emission distribution. Right? That's a this is a proton. That's the the open circle is the deuteron for coalescence model. Red one is for transfer model. Right. So when I have a proton emitted, deuteron also probably emitted. The coalescence somehow deleted a little bit towards the later time. Right. But it's very close. Then also we look at how the deuteron number, proton number is a function of time during the hadronic stage of relatively heavy collisions. So the proton number, right, doesn't change much, and also deuteron number, the deuteron doesn't change very much. Right? So both deuteron and the proton are decreased only slightly with time, early chemical equilibration. I think our problem for the deuteron, because we have a smaller cross section, that's only 10 millibar. Right? And also at the same time, the Sente Cho, the Su Hong Li, they extended the same idea, doing a simple kinetic approach. You have an angle to d pi, then deuteron dissociated into NP, then they start some initial deuteron number, then they evolve by this kinetic approach, assume some fireball expansion for the temperature and the volume of the systems, right? So the only difference, they use a larger cross sections to model the three-body reaction, right? P and pi go to d pi, or d pi d go to p and pi. There's a larger cross sections. Actually, that's cross a maximum value about 200 millibars, right? So there's a larger one, 5 times larger than what we did. And then they found this following: that doesn't matter how many initial deuteron you have, larger number, no deuteron. When you evolve, they all approach the same result. Once you have enough, sufficient large deuteron production annihilation cross sections, then the kinetic freeze-out deuteron is insensitive to the initial deuteron number you start with. That is expected because you're approaching those equilibrium. And of course, there's another approach by Carsten Greiner and his collaborator using so-called Saha equation in nucleosynthesis, right? And the idea is very simple. You assume that you got in chemical equilibrium at all during every time of the hadron evolution. Therefore, you certify that chemical equilibrium condition for the deuteron chemical potential equal to the proton chemical potential, neutron chemical potential. The triton chemical potential equal to the proton chemical potential plus twice of the neutron chemical potentials. Then they assume the hadron will expand isentropically. Therefore, you can determine the chemical potential of proton, neutron, and so on. Then you can determine the deuteron chemical potential. Therefore, in that model, the light cluster, like a thermal model, except add a chemical potential here, the fugacity parameter. Right. Now, if you do this one, then the dependence, the ratio, the T and the chemical freeze out, that the ratio is given by that expressions. There's a binding energy that is very small, so you can, right? You can forget of this factor. It's very small, right? And this is a change very little, right? Because right, it's different from thermal model. Right? If you do thermal model, if you don't put the chemical potentials, then these factors. Then here's the mass. So that's suppressed, right? If I do the, excuse me, thermal model, the kinetic result without chemical potentials or fugacity for all the nucleons, then the thermal model will underestimate. The only way you have to give the fugacity, additional fugacity for the proton neutron in order to maintain the dp ratios. That's the same idea, I think, used by Rob and his Chinese collaborator, I forgot his name, right? He said, I do the thermal model, including this Fugazi parameter. Then he can also get to the NA at the kinetic phase out equal to the NA at the chemical phase out, right? And this is just Kastner's calculation. See, it doesn't matter. Once you're including that conditions, chemical equilibrium, doesn't matter what temperatures. The ratios independent of temperature anymore, right? Because the chemical potential takes care of. This is assumed entropy doesn't change, right? If entropy changes, there will be a little bit of modifications. Of course, now we also know this model, more newer calculation by the people working on SMASH and with Hannah Peterson. Now she's called Hafner, right? And they essentially show the same thing. Doesn't matter. They do the transport model like what we did all days with the young signal. The only thing we look at the n angle to d pi. Now they look at the pi angle to pi d. That costs 100 millibar they use. With the n to pi d, we use the 10 millibar, so factor 10. Again, they get the same conclusion. Doesn't matter how you started with the initial neutron, the final the neutron number are same. The neutron number essentially remains unchanged during neutron evolution. That's the idea. So it doesn't matter now if this reaction cost is large. One doesn't have to do the kinetic or transport approach. One just do the coalescence will give the correct answer. Because I already showed if you do the coalescence, the kinetic phase out give a similar results at the thermal model at the kinetic phase with those Fugazi parameters for the nucleon. Of course, the most recent paper by Kai Jia and Wang Rui, right? And we are just put our names down there, right? They really try to improve the transport model calculation compared to the matrix calculation using SMASH, right? What they did is, right? They including two effects, right? This is called the non-local many-body scattering because in that one, they including the neutron nuclear function there. Now they ask a question, if a two nuclei during kinetic, the transport approach, when put out neutron, they interact to form a neutron and the pion, in terms of pion, pi and n go to pi d, then they ask the question, how those two nuclei, the wave function overlap with the neutron internal wave function. So put that additional factors. And they approximated the matrix element, that's a transition matrix element, using the quasi-elastic approach, impulse approximation. That means the pion comes in, interacts one of the nucleon, change that nucleon into a virtual nucleon, and that virtual nucleon recombine with the spectator nucleon to form a neutron, right? So therefore, they have two effects. One, they have this part is similar to in the SMASH. They use 100 millibar. They use something of the similar order of magnitude, but they have additional this structure of the neutron up here that they ask questions in the SMASH calculations. They don't care. The vegan thing never appear in the kinetic transport approach. And they show you can describe data very well, like in BRIC, HC, and even for PP, right? And that's a proton, deuteron, helium-3, proton, deuteron, helium-3, the experimental data, the theoretical calculations. For PP, they use NPT model. Here they use a hydro, right? Music is a hydro plus hydro. Then they converted into, after hydrogenization, converted into kinetic approach following this transport model, right? And for the PP collision, they use MPT, then after hydrogenization, they put it into the kinetic approach. And they also can explain the neutron production and helium-3 and the triton, right? And also they point out for small system, like PP collisions, If you want to neglect the Wigner function, that's a point like, you overestimate the helium-3 productions. That the size matters. When PP collision, the fireball size is comparable to the deuteron size, maybe a little bit larger, therefore the size matters, right? I'll mention that later on again. Now this one, I raised a very important question, the following. 2 questions. We know deuterons are binding at 2 MeV. Can deuteron bound it in a hot hadronic matter which has a temperature of above 100 MeV? Of course, that's a famous paper by T-Pel and Blaschke and Walter and Ruperger. I think Ruperger is the main person, right? They do the many microscopic quantum statistical approach with relative mean field model. Then they take into account the Pauli block and the so-called Marty effect due to Pauli. For them, the deuteron. Deuteron are the relative wave functions. If they go to momentum space, they have a momentum wave functions. If you have in a nuclear matter, if those moments are occupied, you have to remove those wave functions away. Then the remaining wave function may not be sufficient to make the deuteron bounded, right? So they take that into account, right? The Marty effect due to Pauli blocking, right? So therefore, you have to use, therefore, the deuteron examples, right? The normally free space, the deuteron binding energy, 2 MeV, right? Deuteron binding energies. Now, if I look at 20 MeV, right? Deuteron can be bounded up to something like a 0.005 normal density, nucleon per cubic Fermi, right? So if you go to even higher temperature, you only have nuclear matter, then of course you can make deuteron bounded. The reason is because of higher temperatures, deuteron move faster. Therefore, the internal wave function, the moment may be blocked by the median nucleons, but they move faster. So relative median, those wave momentum will not be blocked, therefore can survive. Therefore, at high temperature, the deuteron, also for helium-3 alpha, they can survive at higher density, right? At higher temperatures. But those are due to the Marty effect, right? But that's another interesting, I have no answer. Now, what the nightmare we're talking about is the hot pion gas at the RIC HC. The nucleon number is small, most of the pions, right? The nucleon pion ratio may be factor 100, something like huge factors. Therefore, what is the deuteron properties or helium-3 properties and so on in the hot pion gas? Are they still bounded, right? In other words, deuteron is bounded by one-time change potentials. Will that one-time change modified by the other pions in the hot matter? Nobody has started that one. So that's one question. Will deuteron or other night nuclei bounded at high temperature, right? With a very few number of nucleons, most of the pions. So that's open questions. Now, another question is formation time, right? We know that 2 reactions, when N go to pi d or pi n go to pi d, right? So when N go to pi d, right? Normally in transform, assume that everything is instantaneous, right? Even an elastic scattering was instantaneous. Therefore, you one collisions, then you propagate it and make another collisions. We never raise the questions. Even an elastic takes time. An elastic, the typical time is the the range of nuclear force divided by the relative nuclear momentum, right? So it should be of order of 2 Fermi or so, right? Or even longer. But we normally neglect that effect. So naturally, so therefore, transformer will work at a low dilute system as a Boltzmann limit, right? Once you go to dense system, we have to be careful, right? Maybe one reaction is not over yet, right? Another particle was scattered again. So that we have to pay attention to. In particular for the deuterons, right? There are the arguments, right? the energy time uncertainties. You just look at this reaction and then go to pi d, right? So the deuteron, right? The two deuteron rest. Therefore, you have energy violation uncertainty of 2 MeV, the binding energy, right? Therefore, from energy time uncertainty, the h bar over 2pd, the 2 doesn't matter, right? So without 2, it's 100 Fermi over C. With 250, it's a long time. In other words, using this naive argument, you have 2 nuclei on the rest, right? They can form deuterons. Of course, you have to set energy or conserve, right? You have to need some something to conserve. But initially, you have to get rid of those virtual energy 2 MeV, and that will take a long time to get rid of. That takes the Fermi. That's a naive approach. And then that Pavel and George Birch in that 1991 paper, they said that is not quite right because not the nuclei are not at rest in hot and medium turn out corrected by the kinetic energies. You conserve the momentum, but the energy you have to increase the energy of the deuteron, the nucleons. Then there's a temperature effect. Now the 20 MeV is about 4.5 Fermi. You just put the numbers in. At 140 MeV is 4. So if you use this argument, that's very good because the deuteron formation time is very, very short, right? And of course, that's another approach called time delay, right? That's against Pavel and the Scott. That's not the original applied to N scattering, right? N scattering takes time. One of the times the range of N try to divide the velocity of the two relative to two nuclei. That's normally about 1 or 2 Fermi over C, right? Then it depends on the phase shift of the two nuclei scattering. That's energy dependence. Therefore, it's given by here. The phase shift of energy is given by this exact formula, given by this formula, right? So this slope is the time delay. So that's about 1 or 2 Fermi over C, the delay, right? So you delay a little bit. Over here, with the high energy, there's no delay because that's just 0 now, right? So there's a time delay, right? Energy elasticity takes time. Now the question, how to apply this to scattering between a virtual nucleon and another unshared nucleon, because in one of them has to become virtual in order to conserve energy. And virtual, off-shell, and in the pi angle, the pi d is the same thing. A pi scatter with 1 nucleon, change that nucleon into a virtual nucleon, then combine with the other nucleon, go to deuterons. That virtual nucleon, off-shell nucleon, and nucleon, they have nucleon potentials. So there's also under scattering going to phase shift. But how do you define this? Phase shift become complex. That's why Kai Jiao showed this figure, right? You calculate phase shift, the rate of phase shift is imaginary. Has a infinite, right? At pole, that's a deuteron pole. The deuteron, and N has an imaginary momentum that corresponds to bounded deuteron. That's an infinite, right? But that's the imaginary part of the infinite. So does that mean as an infinite time delay? Maybe it is because you have an N, right? And they never scatter out. They're all bounded into deuterons, so never over. So that's an infinite delay. And some anonymous guy claim if you calculate using a red curve, right, then you get something like a 100 Fermi over C, right? That's a radical approximate curve, right? That's about 100 Fermi over C. Then that's bad. If deuteron takes 100 Fermi C to form, then how could we can talk about kinetic theory for deuteron productions? And the Kai Jia and Ray, they estimate the deuteron from using this formula. 1 over p pi is the time for that pion nucleon scattering, change a nucleon into off-shell nucleon, right? No, pion scattering takes this time, pi over lambda. This is the time for the pion traverse between the interaction radius. Then the pion go to delta, so you have the delta time. So they estimate about 3 Fermi over 3 Fermi is pretty good, right? Because that's comparable to the nucleon elastic scattering time. So everybody don't bother that much by nucleon. You are scattering in the transport model. One shouldn't worry much using treated this kind of reaction in the transport model, because after n to pi d or pi n to pi d, then takes a 3 Fermi over C for deuteron to form. So that's not too bad approximation to treat by the transport kinetic approach. I have another approach. Maybe I'm getting too late, and let me go quickly, right? I use a time-dependent perturbation theory, right? And I think I can time is late, so let me skip the details, right? Because I said that it must depend on matrix elements, right? So I can calculate the time for that transition from pi n go to pi d using this time Fermi's golden rule we'll calculate. Unfortunately, that one, depending on a volume, I can relate it to the annihilation cross-section for deuteron, but relate to the volume, because in the cross-section, you need the waveframe normalizations. So that volume, if I take as the size of the inverse of the pion mass as the radius, and I get the volume about 12 cubic Fermi. Then I use this cross-section, pi d is huge, here 200. So I put that back in, I get a 7 Fermi over C. So the factor 2 larger than, factor 2 larger than Kaija and the one race calculations. Of course, if I use 12 cubic Fermi, my NN elastic scattering time also is too long compared with the estimate from phase shift as a function of the energies. So I have to reduce this by half, the 6, then I give 3.5 consistent with Kaija's. But here, everything's there, right? I introduce, you have a matrix as there. So all the interaction are there, right? I have not on the pi n interaction, change that nucleon into virtual offshore nucleon. Also include the virtual offshore nucleon, the nucleon evolve into deuteron. That takes time. It's everything there, but depending on this volume, will the two nucleons interact. But anyway, this is under debate. Just that if any people has a better idea, I would appreciate it very much. Now that's just an old story. Coalescence might give a natural explanation of the suppression of nadir put at a high at a small system. So here that's the centrality, that is the central collision. Then you go to the multiplicity, right? Then you go to the very peripheral one, have very small particle, you have very small fireball. Then there's a suppression. The coalescence model can naturally explain, right? As I already explained the PP collision in the previous slide. Right? So, because that takes into account the relative size between deuteron, triton relative to the fireball size. Right? But in statistical model, that is not there. You have to artificially introduce a very unrelated large canonical correlation volume to suppress the thermal production of light nuclei in small system. Now, I really want to let me skip the hypertriton. I think that is the work done by Zheng Zhang with me when he was with me. The interesting with hypertriton is hypertriton is weakly bounded, especially lambda. Right? Lambda only is bounded by 130 kiloelectron volts, has a huge size. Right? There's a lambda wave function. Right? Lambda has a radius 10 Fermis away from the deuteron. Lambda looks like a hammer. Right? We are like a handle, the end of the hammer. Right? So it's very large. Right? So I think for hypertriton is probably questionable to discuss its evolution in hadronic methods. See, that 10.6 is a huge volume, right? You take a 4 pi over 3, it's a huge volume. There are so many pions inside that hypertriton. How can one talk about hypertriton produced from empty lambda to hypertriton plus a pion on the reverse? I mean, it doesn't sound reasonable. Therefore, to coalescence model, right? Zheng Zhang showed hypertriton is insensitive to the kinetic. At the careful, that's the hypertriton number. You start to the coalescence 15 Fermi over C. You don't do anything. After 15 Fermi in the proton, neutron, lambda, They free streaming after 50. Then you do the coalescence, only change very little, all right? Because of the larger size. So most of the hyperdynamic probably produced 100% after kinetic freedom. Although proton neutron, they stop scattering, lambda scattering, pion scattering, but hypertriton and the pion, the interaction is still there because they are large volume. So that's the best way to test the coalescence model with the hypertriton. Now, finally, I'm already 1 hour, sorry. You have seen this before, this idea of Kai Jia, Li Wenqian, and Zhang Boxu. They said that from the beam and scan of the deuteron, this ratio, right? Triton proton of a deuteron square, which is sensitive to the neutron density fluctuations. So the data from SPS data, someone thinks that's a peak over here, right? And also the Rick, you also say something over here, right? Rick, unfortunately, said that if you assume that formula, using this formula to fit the star data, extracted the neutron density fluctuation peak at the 20 GeV, and the SPS is a peak at about 7 or 8. So there are 2 peaks, right? So we have to see eventually how the 2 experiment data reconcile with each other. Maybe there indeed are 2 peaks, maybe only that's a broad peak. And that can be, if one just do the normal transport model calculation without anything, right? You just run GEM, right? Which is some simple cascade models, or you run the hydrodynamic model, follow URQMD and do the coalescence, or you do MPT after the end, you do the coalescence, or this also is MPT model, this from UGAM, at least the other group, GEM, hydro, and MPT with coalescence. There's no energy dependence in that ratio. Triton number times proton number to a deuteron, that's flat, right? And that's right. They got some structure here. They got some structure here. We have to much better understand. Right? 3 to 1, so they are in disadvantage. They have to convince 3 of us, right? We only have to convince Margan, so it's easier for us than for Yugang. You have to try to convince us, okay? Now, that's the last few minutes, right? That's an old calculation by, that's a calculation, I think, by Kai Jia. He shows that in the NGL model, you have the temperature, the number, the mechanical instability because the derivative of pressure with the density is negative. That when you compress the matter, the pressure decreases. That's called mechanical instability, spinodal regions. And with that, and that is Fan Li when he did a calculation. One without the spinodal regions, he stopped something. At the end, right, there's not much. If we started with quark methods, you evolve through the spinodal region, you get large density fluctuations. And that idea was later on picked up by Kai Jia, and he showed indeed you do an MPT model, initial conditions followed with angel transfer model, then followed with the art model MPT, then do the coalescence. Indeed, when you have a spinodal region, if the trajectory going through spinodal region, you get this the ratio triton proton over deuteron square. If without the spinodal region, it's this one. So we're talking some effect, right? It's a 0.4 here. This is 0.5. We're talking about 10.1 of the 0.4, 25% effect, right? So, and of course, it's hard to see compared to this one, right? Here, means this dense structure is much larger here, but somehow you look at the coalescence model, get the triton proton deuteron square, you only get 25% effect. The question is, those effects sufficient to explain this experimental data, right? So the idea eventually was hopefully there's some dynamic model. One can change the equation of state, try to fit this measurement, right? And to see what kind of equational state we need in order to reproduce this peak. So let me summarize. Right? Well, that's why let me skip the multiscale light nuclear production that we did with the 小分 low and the wave in zao. Somehow that's a very interesting behavior. This ratio depends on multiplicity in that behavior, and that can be understood with the schematic approach, just as a fireball, right? And then you can see when you go to smaller system, you enhance it, right? The larger system, you can understand what's the origin for that one. So let me summarize. Coalescence gives similar light nuclear yields in heavy collision as the thermal model if the binding are small compared to temperature of hadronic matter, and their thermal wavelengths are much smaller than the size. Both are results similar to that from transfer model study in which deuterium are assumed to remain bounded and can produce until. But that's important. We assume deuterium are bounded, a triton also bounded, and can be produced and dissociated. So that is, I think, is still a question, particularly of hypertritons. This, I think, is a nice part. Coalescence can naturally explain the suppressed production of light nuclei in collision of small systems, because that model automatically takes into account the finite size of the light nucleon compared to the size of the fireball. Hypertriton is expected to be produced significantly later after the nucleon lambda have frozen out because of its larger size and small binding, right? Otherwise, even if produced, the kinetic field would be dissociated right away by the pions. Pion is simply too large. Right? Even the kinetic field to coalesce, you produce a hypertriton, a nearby pion would destroy the hypertriton right away. Right? If the hypertriton is produced. So I think hypertriton is really produced much later than the kinetic field out. The nuclear density fluctuation enhances the production light nuclei per a possible explanation of the observation SPS and RIC, but let's just assume that's the mechanism to leads to enhance the production of triton, proton, the deuterium square. Then you can track the deuterium density fluctuations. Whether that's correct or not, we don't know. So to quantitatively extract the quark matter phase diagram from the beam and its dependent on light nuclear yield ratio, definitely remain a challenge. I hope eventually the more quantitative study can be developed. We need a very flexible equational state, either in the transport approach or in the hydro approach, then to study whether density fluctuation or critical fluctuation can lead to enhance the production of light nuclei yield ratios. Then we can compare experiments to extract that equational state. What is the critical temperature, critical chemical potentials, whether indeed that's a first order phase transition between QGP and hadronic matter leads to a large density fluctuation due to spinodal instability. Thank you for your attention.
Thank you. 好，谢谢。刚才这个柯老师给了一个非常精彩的这个 overview 的这个报告，来介绍这个 Coalescence 是这个对这个重离子这个物理里面发展的历史以及现在的一些林林总总的发展啊，包括受益模型、热模型的一些比较，还有最后也介绍了这个用来这个氢离子这个 double ratio 的研究可行的项目啊这些信息。那么现在看大家线上的、线下的对这个柯老师的这个报告啊，有什么一些问题，大家可以提出来。
柯老师您好。
啊。
柯老师你好，我想问一个问题，就是这个统计因子这个 statistical factor， 就是在什么能区我们应该就不考虑这个 isospin effect？ 当能量到什么时候应该就需要去考虑它呢？
哦，你说在 Coalescence model 前面那个 isospin factor 是不是？
对，是不是在能量比较低的时候、低能的时候要考虑这个因子更合适？
不，这看你怎么讲嘛，对不对？ 如果你真正做 naive 的 coalescence model 的话，你应该 introduce isospin factors， 对不对？所以 neutron 我们普通用 3/4， 那从 spin 就2个 proton neutron spin half the proton neutron form 一个 spin triplet spin 1的 neutron， 因为 include isospin 的话，应该变 3/4 应该变成 3/8， 差了 factor 2在那边，对不对？
对。
这做你真正要是做这个 coalescence model， 但是我们知道 coalescence model 是一个 approximation， 对不对？我 Pn 可以变成 neutron， 但是我 Nn 也可以变成 neutron， 因为 Nn 因为你要 balance energy， 一定有一个 particle 在附近，对不对？
对。
所以你是 3 body， 所以我不是在 transport model 你是 pi Nn go to d pi， 在那个时候呢 proton neutron 什么都可以产生 neutron。如果这个 eventually leads to thermal equilibrium, thermochemical equilibrium with finite fugacity of nucleons and the neutrons， right？ 在那个时候呢，跟 thermal model 一样，在 solar model 的话，你就不要 statistical factor， 懂吗？所以因为 coalescence 你做一个 approximation， 所以你要摆，但是你要知道 coalescence eventually approaching 这个如果我们 believe transport model assume neutrons survive can exist in hadronic matter， 要可以产生个不大型，就 approaching thermochemical equilibrium， 那时候呢就没有 isospin factor， 所以呢，如果我们 take 那个 attitude 那个 opinion， 就是说我的 coalescence 是个 approximate treatment， 所以 eventually 我 have to reproduce transport model approach 或者 statistical model approach 或者 Saha equation approach， 那我就不能有 statistical factor， 但因为你 coalescence 是一个 approximation， 所以呢，你不能 purely 就用 statistical coalescence model 来做它。
好，谢谢。好，看看其他还有什么问题没有？你说是线上是吧？对。刚才老师举手了。哦，看看王军老师是吧？
哎，对，于刚，哎，
好啊，你好。
哎，柯老师你好啊。
你好，你好。
我可以问了是吧？
需要你问。
对，
没问题。
好嘞，那个就是我的问题是你在做这个 transport 的那个，你比如波尔兹曼方程模拟的时候啊，
对啊，
你是把它放在一个盒子里头呢，还是放在一个自由空间？
自由空间，所以 system expanding。
哦，他自己
no 呀，我那个 density fluctuation 那一个，我是放那个 box 里。
那为什么有的时候你放在一个 box 里头，有的时候你放在一个自由空间？
我要以 no。这要跟实验比的话，你最后需要跟 heavy 肯定你要让它自由空间。我要讨论那个 physics， 假设我 start 一个 nuclear matter， 如果一开始我是 uniform 的，但是我在 spinodal region 里面，我让它 evolve density fluctuation 就会产生。
就说你是根据你
研
究的这个对象 observable 来就是来选择是放在自由空间。
像这个呢，这个是摆了一个 box， 这个是摆个 box calculation。
对，我就是。
所以这个 density fluctuation 很大，你看到没有？但是孙凯佳把它摆到一个 free expanding， 就是说我从这边开始，又在 develop density fluctuation， 又在 expand， 效果就小了很多。
是这样，
就是小了很多呀。如果我能把那个 Rick 产生的 matter 把它 confine， 那你 density fluctuation 就可以一直在 develop，对不对？就给他们讨论 first order critical point 一样 ，critical 一个 critical slowing down 嘛，这他们很 worried 的，对不对？你到了 critical， 你根本不能 approach slowing down， 因为 system 那可能已经 expand 掉了，所以你根本达不到那边。如果你把 quark matter 那个 critical point 那个 critical QG 不把它 confine 的，你如果将来不知道有什么办法用那个 infinite strong 的那个 magnetic field 来 confine 它，那你就可以让那 quark matter 它一直在 evolve for 1 hour， 那它当然会达到 critical point，对不对？
Okay.
就我们没有人讨论，我们要多 strong 的 magnetic field 能够 confine 我们的 quark matter。
好的。
很小个 region。In principle 可以，我没有，你先 estimate 一下的。我要多 strong 那个 magnetic field confine 我们的 quark， 那真的不 expand。 就像人家现在不是很多人做那个 trapping 嘛，你把这个 nuclei trap 在一个 trap 里面 magnetic trap 里面，然后你就可以 study 它的 property，measure 它的 mass， 还有 measure 它的东西很 detail， 你可以 measure 比如 neutron， 他们连 neutron 都可以 trap 起来的 measure neutron 的 lifetime， 不是最近是要量很 accurate neutron lifetime measure 把它 trap 起来，对不对？但是呢，如果我们能够有办法，这个我们 produce quark-gluon plasma 把它 trap 起来，它不能 expand。
对，那就是等于放在一个盒子里，对吧？就是
放在盒子里。对呀，那个 magnetic field 要多大我不知道，可以 estimate 一下。假设我现在一个 quark-gluon plasma，对不对？然后我要多大的 magnetic field？ 但是你不能是 uniform magnetic field， 你要有那个让这些 charged particle 在那个绕着我的 external magnet 在那边绕，就不出去了，对不对？就在那边绕，对不对？在那个时候呢，你就可以 trap 它，对不对？不是你们很多人在做 NGL， put NGL 在 magnetic field， 在我这那个什么华美也做，很多人在做，连那些做 lattice 的人现在也把那个 QGB 放在 magnetic field 里面，对不对？但他们都是 uniform。
对，他这个就是说，他是理论的这个理想。
但是应该 study 什么？应该 study 那个什么 magnetic 不是 uniform， 就是我要在 external 加个 magnetic field 进去。
对，就是
当然我不知道，像我们 estimate 我不知道多大的 magnetic field， 我可以 confine。我们知道在 fusion reaction 我们可以 confine 这个neutron 跟那个triton 做这个 fusion reaction， 对不对？我用 magnetic field confine 它。但 quark-gluon plasma 不知道怎么 confine， 用 magnetic field confine 要多 strong。
OK，
那就有意思。
谢谢。
好，那个线上还有李阳是吧？举手了，是李阳吧？喂，线上有举手的是李阳还是谁？请问。李阳，这是李阳。我不知道那写的李阳是谁啊？请问啊。那就是何猛呢？何猛，请。
何明啊，你好。
柯老师你好，马老师你好，柯老师你好。喂，柯老师你好。我想问一下，就是您开始提到的这个 thermal model 做这个 light nuclei production at the chemical results， 但是您做这个 coalescence 在 kinetic results 得到的这个 production yield 几乎是一样的。然后这个可以由
我要做 kinetic freeze 做 coalescence。kinetic freeze 做 thermal model， 那时候你要用你的以前的老板 Rob 的 idea， 加上 chemical potential proton neutron chemical potential 在 kinetic freeze， 这时候 thermal model 跟 coalescence model 是 identical up to the binding energy correction。
Yes， 所以这个可以由这个 partial chemical equilibrium 来解释。
就是
说或者说一个 very large 这个 2-3 core section to maintain the partial chemical equilibrium， right？ 但是我想问的是，
就当然说，如果你 cross section 大一次 cross section 的话，你就在从 TC 到 TK 呢，它 always 保持 partial chemical
to maintain the partial chemical equilibrium。
这就是那个。
但是我想问的是，但是我想问的是，如果做 coalescence， 如果在这个 chemical freeze 做 coalescence 呢，得到结果肯定会不一样吧
？chemical freeze 做 coalescence， 我好像谁做过的那个沈凯佳，那时候应该是一样的。
因为你的 density， 因为这个 proton neutron 它的 density 在这个 chemical freeze 会大多的，那时候体积会减小，因为从 chemical freeze 到 kinetic freeze 这个 volume 在 expanding， 那么开始的 density 更大 ，coalescence 得到场合可能会大得多。
因为你在任何 temperature， 你做 coalescence 跟那个 thermal 都是一样。所以我在 TC 的时候我没有 chemical potential， 所以我在做 coalescence 的时候呢也没有 chemical potential， 所以 thermal model 还是一样 up to the binding energy correction 也是 identical。唯一的不同就是看你要不要 including the resonances。你在那个chemical freeze 有很多 resonance 在那边 ，proton neutron 很少，都放在 resonances。因为你 thermal equilibrium with respect to resonances， 在 kinetic freeze 的 resonance 都不见了，很少，对不对？所以你跟 proton neutron， 所以你在 TC 的做 Coalescence 跟 thermal model 做的话呢，还是一样，但是呢，我觉得还是一样。你只要我知道 proton number、neutron number， 给我一个 temperature， 那个时候 chemical potential 这两个 model 给你 identical up to the binding energy corrections。陈凯佳可以 correct me， 我相信是一样的。如果我在 TC 如果我知道 proton number、neutron number， 我要做 coalescence 跟 thermal model 也是一样 up to 那个 binding corrections。OK，
对的，就是那个统计因子，如果是两个 model 是一样的，结果就是一样的。
right，
但是 naively speaking， 这个 proton neutron 它的 density 会下降啊。
不，你在 TC 的时候 就是你在沙海 equation， 那就 assume every time step 都是 chemical thermal equilibrium， 那 dp ratio 根本就不变， 对不对？如果你 entropy 不变的话，就完全是一样的。这就是那个 Carlson Griner 说的，然后用沙海 equation assume， 所以它不管什么 temperature， 对，它的 thermal model 跟它是做 thermal model， 对 ，chemical thermal equilibrium，partial chemical equilibrium。但是呢，孙凯佳也 proof 了，对不对？那个 partial chemical equilibrium coalescence model 呢 give the same results up to the binding correction。
我可以补充一点，就是那个何明，
那
个它那个 density， 就膨胀，它 density 是确实是会降低的，但是还有两个 factor， 一个是它温度也会降低，另外呢，就是有很多那个 resonance， 它会比如说 delta resonance， 它会 decay 到那个 proton， 所以呢，它就是总的来说呢，就是你导致就是它丢穷的产额在那个 chemical freeze out 之后呢，它就不变了。这个也是为什么就是你通过 transport model 也能发现这一点，就是可能就像寇老师说的，可能是因为它那个 entropy per baryon 它不变了，所以导致这个 D to P ratio 呢也就不变了对。
OK， thanks。
下一个。
对，像刚才提问的那个，请你把话筒打开。
好了。我是李安
是吧？对，李安，你请讲。
谢谢柯老师的报告。我有一个可能非常naive的小问题，就是温度对那个会不会有关键作用？因为我看前面的对相图的计算70 MeV， 以及后面对那个 crossover 和 first。
你说我那个的，你说这个相图是不是？
都是在70 MeV。
这是这张图吗？是不是这张图？
对，这张还有后面。对，这个时候有一个 model calculation， 一个是 first order， 一个是两个都是
first order，
加那个
都是 first order。就是 NGL model 的缺点就是说它的这个 critical point temperature 很低，懂吗？如果记得当年何明不是做的 Schumer Dyson 嘛 ，claim 这个 critical temperature 应该差不多100多个 MeV， 对不对？现在这个什么 NGL 是很小，所以 NGL 缺点就是很难变，就是孙凯佳 structure 很小，怎么样的我怎么 move 这一点，还有这个在这个 phase diagram 怎么变，因为我们现在不知道这个 critical point 在哪里，所以最好的是呢，我有一个很 general model， 随便我怎么变，然后把这个 phase diagram 摆到不同的那个 hydronic 好，或者是 transformer 的好，来算这个来那个 double ratio， 然后去跟这个实验从这边 track 的那个 phase diagram， 这是那个是最好。NGL 可能不太好，就是因为它这不容易很难变，你要把这个移了过来很难移，孙凯佳 structure 的各种方法很难移，不 flexible， 所以可能要把这个 give up， 就是我们完全不管这些，根本 forget 是 NGL 什么东西，我就用手摆，我的 artificial 的就 construct a model 呢，就是我可以这边随便我摆，对不对？但你还有一种 approach， 就是我就如果 take 这个 Schumer Dyson approach serious 的话，那个 functional renormalization approach， 这个他们有 definite predictions， 对不对？然后把它 parameterize 摆到 hydro 里面，或者摆到 transport model， 然后想办法去算的 light nuclei production， 然后去跟实验这个不应该算 delta， 应该算这个 ratio， 对不对 ？try double ratio， 就跟实验比，看哪一个 equation state 能够给出这个 structure 来，然后你就说这个是 properly correct equation state。NGL 可能不是 not the best way， 因为 NGL model 不 flexible enough。
就是我能不能再接着问一个一个小的 point？
Sure
谢谢。对，因为那个 critical 的各种 model calculation 里都是在，意思是就是零温，完全是 zero temperature 的时候，大家都
这不是零温啊，这是 finite temperature， 这不是60个 mV，
对，它就是
critical point， 60个 mV 0.8个 net quark number density， 这是 critical point。
对，因为那个 phase diagram 上面就是有些地方它发生了一阶相变到 crossover 的一个变化，那意思是说，大家现在 community 都认为，在绝对零温的时候，一定是一个 first order transition 吗？
零温 ？What do you mean by 零温 ？Zero temperature？ 如果
零温
不，这个不是的，要画 phase diagram 也是这个东西啊。你普通人家说这边是 smooth 的，对不对？这边 smooth 的，然后这边变成 first order， 对不对？这边是 smooth crossover， 到这边变成了 first order， 怎么下来，对不对？普通我们用这个 mu， 我们这边用 mu 就是不用这个 net product。你用 mu 的话，你看不出这个东西来，懂不懂？你要画 density 才看得出这个东西来。你画的是这个 mu q， 那你看不出这些东西来了，对不对，申凯佳？
就是现在那个
如果画成 mu q， 这个图怎么变？
就一条线，就是一条线，然后
这变条线
啊，对，
就是这样，这是 smooth crossover， 这边是 first order transition， 变这样，懂吗？
对，说温度
就是 critical point，
它就是变成 first order 了。所以，因为我比较感兴趣做致密星的计算，致密星都是非常冷的，没有那么
你要到很 low temperature， 对，那呀，你是在这边，对不对？你要很高的 density， 非常 low temperature 在这边。
对，我们可以
你是在这
first order 那个。
你们有 first order transition， 那边都有的。你在那个 neutron star 里面，那个 transition 多半是 first order transition， 从那 hadronic matter 到 QGP。quark matter 多半是 first order transitions， 也许不知道，也许你 go through 那个 quark-ionic matter， 你听过人家讲吗？你可能在 neutron， 现在很多人 study 那个，在 neutron star 里面，它从 nuclear matter 变成 quark-ionic matter， 然后再变成 quark matter， 3个 stage。quark-ionic matter 就是说，这个quark 来 carry 这个，里面还有 meson，quark-ionic 就是 mixture of quark 跟 meson。就你 baryons 就在 nuclear matter baryon number carried by nucleon， 到 quark-ionic 的 baryon carry quark， 但是你 meson 还在，还有 meson， 然后你再 raise temperature 很低，然后你的那些 meson 也 dissociate into quark。现在好多人在用这个 quark-ionic matter 来讨论这个 neutron star 的那个 properties。
对，以及是用 crossover 来做那个混杂性里面高密的像图，包括 Golden Bay
那边大概不会有 crossover， 因为你在那个 neutron star 那个merger 里面的neutron star merger temperature 蛮高的，刚开始，对，我不晓得，你比我要熟。但 neutron star merger 一开始 temperature 都高。
对，新生中子星。
我不太懂。
谢谢柯老师。
好，那最后我们请线上黄焕忠老师好像有提问。
焕忠啊，你好。
焕忠。
啊，你在哪里？你在 UCLA 还是在中国啊？你在哪里？
我在 LA，
你在 LA 啊 ？OK。
对，那个呀，王老师你好，那个我也简单，就是因为在这个 proton 这个 liquidity distribution 随着这个 beam energy 还是变化挺大的。那么
对
Coalescence 之下的话，它是个非线性的，这个造成了这个 deuteron 和 triton 的这个 liquidity distribution 也会随着这个快度变化更大，因为它是非线性的一个效应在那里。那在这个在这情况下，就是假如我们看就是proton triton 比上这个 deuteron square 这个 ratio 的话，会不会受我们实验当中这个宽度的这个限制的影响，造成了这个随着能量的一些变化？就是说我们就是在实验上还有其他什么方法能够独立的来去这个验证一下这个物理图像，就是到底有没有这个由于这个相变或者有 critical 时候会造成的一些这个效应在那里。
那个
他们不是他们要 study 这个 proton fluctuation 嘛？就你们这个实验那个徐璐最有兴趣的 net proton fluctuation 啊，你也可以讨论。但你 impression 你可以讨论 net deuteron fluctuation， 但是那个 number 太少，所以你不好做。Every event 不到一个 deuteron， 对，所以你那个 fluctuation 看不出来。
主要是你这个 peak 在15个 GeV 左右，那它那个 peak 在更低了，所以这个现在是不是很清楚。
对，因为那个 net proton fluctuation 很奇怪，你也听到上次谁在讲，对不对？上个礼拜那个因为什么？你到了 low energy 之后，你在 high energy 的话，你量的是 momentum space， 因为那个 Buchanan 那个 flow 把你的 coordinate space fluctuation 变成 momentum space fluctuation， 所以你可以看得到。但是你到了那个 low energy 的话呢，没有 Buchanan flow 了，所以你 spatial fluctuation 呢从 momentum 看不出来的，所以呢那边要 be careful， right？ 因为你量的都是在 momentum space， 不是在 coordinate space。你只有在量 deuteron 的时候呢，把这个 coordinate space information 摆进去了，因为 deuteron production depends on proton-neutron relative distributions， 所以呢，它的information在里面。但是受不受 rapidity 的影响，你现在就会说如果我 change rapidity，
因为 proton
有什么影响？
这个proton liquidity 随 energy 变化还是挺大的。
但是问题是 coalescence 因为 involve proton neutron 到非常 close in momentum space， 所以它的 rapidity 的 spread 很小，就是两个 proton neutron 一定要很 close in rapidity spin， 它才能 form deuteron， 不然它不能 form deuteron。
非线性的效应就是说，它那个假如 proton rapidity 变窄的话，那 deuteron 会变得更窄，就是因为
sure，因为你 square 它，对不对？对，你原来是1除到 0.5， 一个是 peak 在1，下面 0.5， 你现在丢上要 square 1，一个变 0.25， 大了1倍了，对不对？所以你们没有 check 过吗？我没有 look 过。你们实验 data 看 proton rapidity 是不是 deuteron rapidity 的 narrow 多了？有没有这个先看到？你要这个罗小芬应该去 check 啊，因为他专门量 deuteron 的。check rapidity
在 PS1 能区，我们只能测就是中心快速区，没办法，就是没有测 DNDY 的分布，这个它有统计的原因。
统计原因。
而且
proton 你可以 proton 你可以，对不对 ？proton
在 high energy 的话，它
不是你在 beam energy 在10个 GeV 没有 proton DNDY 吗？你有吗？没有吗？
主要是接收度，主要是它那期接收度没有 cover 那么大的 rapidity。
没有 cover 那么大。OK， good， 对，不好做。
0.5。
不然很有意思的，不然你会看到这个 nonlinear effect， right？ 变 narrow 的 deuteron， right？ 这是 narrow 是在 momentum space， 然后如果有 first order transition， 这个就是你这个 shrinking 会不会受到这个 force of phase transition 的影响，这个我不知道，这可以 modeling， 可以去 model 它，对不对？比如我做一个blast wave， 一个是我占 proton 的 dNdy， 然后我看这个deuteron dNdy 这个当然 shrink 了，对不对？如果再加上 spatial fluctuation， 对不对？如果这个 fluctuation 如果跟那个 momentum 间有什么 correlation， 会不会看出来影响到它？可以 model 上去 study 它，就是你这个 idea 可以 check， 对。Good。
好，这个时间也差不多了啊，这个感谢所有这个线上线下的这些老师们，最后呢，我们感谢这个柯老师今天这个精彩的报告。